Hello, students. So this is part 3 of chapter 11, and what we're going to be talking about is a type of elimination reaction, the E2 reaction. That's a bimolecular reaction, similar to SN2, but an elimination giving the alkene product. So we'll talk a little bit about mechanism. What's really important here is anti-periplanar geometry, which dictates stereochemistry. The last part of chapter 11 involves just a summary, how to predict what products you're going to get given certain substrates, reagents, and conditions, and then just using that, applying that in synthetic routes. Okay, so E2, again, stands for elimination bimolecular. A strong base is required for this elimination to take place, and it's similar to SN2 because it's a concerted mechanism. So we're going to have the base deprotonate a hydrogen. You form the pi bond with the 2 electrons here in the sigma bond, and then you kick out a leaving group. This is all going to happen simultaneously in a concerted fashion to give your alkene product, the protonated base, and then the leaving group as an anion. The rate of the reaction depends on the amount of alkyl halide and base present. Okay, so in an E2 reaction, you're forming an alkene. So your reagent is a base, and it's going to deprotonate a hydrogen in the beta position. That's different than SN2 because in SN2, the reagent acts as a nucleophile that will attack that alpha carbon where the halogen is directly attached. So here I'm presenting a tertiary alkyl halide, and I have hydroxide. This can act as a base or it can act as a nucleophile. So here's our question. What's going to happen? How is it going to act? And is it going to attack the alpha center, or is it going to deprotonate a beta hydrogen? To answer that question, you really want to look at the substrate involved. So in this case, the substrate is key because if you recall, SN2 reactions, they go through that trigonal bipyramidal transition state. That's concerted. You get that inversion of the umbrella and the leaving group leaves simultaneously. So for that to occur, for hydroxide to function as a nucleophile in a substitution reaction, it needs to come in and attack from the backside where all of these bulky groups are here, this bulky tert-butyl group is. So there's just really a lot of steric hindrance. You would have this umbrella inversion and the leaving group leaves. So the substrate tells you, in this case, what's really going to happen. Just even though hydroxide is small, it's just really hard to get in here into that trigonal bipyramidal transition state. So instead, the hydroxide is going to act as a base in an elimination reaction because the beta hydrogen, the hydrogen off of the beta position, here's alpha, here's beta, is more available to abstract. So this reaction will occur to give the elimination product. Eliminations are regioselective. You've already encountered that in E1 mechanism discussions. And I'm going to show the same thing here. Remember that regioselectivity is about the region where the double bond is going to be located. So you can have the Zaitsev product, which is the more substituted alkene, or the Hoffman product, the less substituted. So if I start with this alkyl bromide, here's my alpha center, but it's the beta hydrogens I can abstract. So there are 2 types. I have 2 methyls here, so these are identical types of hydrogens. And then there's this ethyl group that has a beta hydrogen here. So if you have a small base like sodium hydroxide, it can deprotonate either of these. Preferentially, you will get the more substituted Zaitsev product because the more substituted alkene is more stable. It'll end up having a lower transition state, so easier to climb that hill, lower activation energy. So the sodium hydroxide will deprotonate here, form your pi bond, kick out bromide in a concerted fashion if this is E2, and you'll get this product. You can have some deprotonation of these guys And what's interesting, you're really fighting against the odds. There are 2 H's here, but 6 here total with the 2 methyls. So it doesn't happen to a great extent, because even with all these 6, you only get 29% yield of the Hofmann product, less substituted, disubstituted versus tri, 1, 2, 3. So when you're trying to figure out regioselectivity, what's crucial for you to look at is the base that you're using. The reason is, if you have a small base, like a ethoxide or hydroxide, you could get into that more internal beta hydrogen. So you could get in here, deprotonate, and make the Zaitsev product. That's preferred, especially when you have a small base. However, if your base is just too bulky and big, like these 2 guys, then it's really hard to get into the center just because of sterics. So it'll pick off the beta hydrogen off of these methyls more, just because they're more accessible, less steric. And you end up predominantly with the Hofmann product, which is what you actually see experimentally. So just remember, bulky base favors Hofmann product, unhindered or small base favors the Zaitsev product. Here are examples of bulky bases. So if you see these, they're going to favor the Hofmann product. And sterically hindered bases, like these bulky bases, they're weak nucleophiles. So you will tend to get those elimination products as opposed to substitution. Okay, let's practice. So I want you guys to predict major and minor products for each of these E2 reactions. So pause this, take your time, write out all the products, and I will go over it. Okay, so for this first problem, you have this chlorine, and the first thing you want to do is identify what hydrogens can be removed to undergo the elimination. What beta hydrogens do you have? Hydrogens off this carbon and off this methyl group, but not here, because there are no hydrogens. There are 2 methyls and the rest of this ring. So the only places you can abstract a hydrogen is here, forming a bond here, or here. The next thing, look at your base. This is a small base, so you'll prefer to form the more substituted double bond in this position. And your minor product will be the Hofmann product here. Less substituted, the major, more substituted Zaitsev. Okay, for B, identify the types of hydrogens. There's these here, the kind of secondary hydrogens, and then these off of the methyl groups. If you have a small base, again, you're going to prefer to deprotonate to give the more substituted alkene. And so your major product is shown here, minor is here. Just to let you know, you could deprotonate hydrogens off this methyl or this methyl. And so you couldn't write a double bond here, or your double bond could be here with a single bond here. Those are identical compounds, just because you can have bond rotation here. Okay, the last one, what's key to look at is you have a bulky base. So in this case, you actually do want to form the more substituted, but you can't get in there. This base is too bulky, so you can only pick off the more outside, less sterically hindered beta hydrogens off of this carbon. So you end up with this 1-butene as your major product. The minor product would be the trans alkene, the internal alkene here, the Zaitsev product. And just to let you know, if you didn't think about it, you could have cis or trans, but trans is preferred because it's lower in energy. And so it's possible, you didn't have to write this, but definitely the cis is possible, but it'd be very minor. Let's talk about that cis-trans stereoselectivity. So again, you will prefer, if you have a small base, to form the more substituted alkenes, but if you can form cis or trans, the major will be the trans. And the reason is that it's just more stable. You have the trans energy diagram here. The trans is lower in energy because the cis is higher in energy due to sterics. So if you remember from your lab doing the modeling, cis alkenes have hydrogens off of here that can bump into each other. There's steric repulsion here that makes that alkene higher in energy, higher on this energy diagram. In the trans, those groups are farther apart, so lower in energy. Overall, the profile here and the transition state for the trans is lower in energy, so essentially a lower hill to climb, lower activation energy, so that's going to be preferred, and to give the more stable trans product that's lower in energy. Okay, let's talk about stereospecificity. So this has to do with the actual, looking at the actual geometry of the beta hydrogens available. There is actually a very specific orientation of the orbitals. There needs to be a specific alignment where the bromine and the hydrogen, in this case, in this substrate here, are in the same plane, but opposite each other, and we call that anti. So they're anti to each other, but they're in the same plane, so we call it anti-periplanar. And so if I was standing here looking down this bond towards this direction, I would see that the bromine is down and the hydrogen is up. So a Newman projection could look like this: bromine down, hydrogen up, and they're exactly opposite each other. Hydrogen's on top, bromine's on bottom. That's anti-periplanar. Periplanar, again, because you have a straight bond going across to connect behind this carbon to the other carbon that the hydrogen's attached to. You can rotate around this bond and flip this hydrogen A down. So notice there are two hydrogens. I'm specifically focusing on HA, just one of them to just really make this point clear. If I rotate around this bond, this is like a propeller, then I can point the H down. That's eclipsed, and we call that syn-periplanar. So if I was standing here and looking down this bond to here, the bromine is down and the hydrogen's down right behind it. So those are eclipsed right behind each other. That's syn-periplanar. The reason why I'm going through this is your elimination is only going to work if your hydrogen that's being deprotonated is anti-periplanar to your leaving group. So this is really important. So some molecules, if they're locked in place or don't have available hydrogens, the elimination is not going to occur. If you cannot get into this anti-periplanar geometry, it's not going to occur. So I'm going to show it here. This is just the same thing here that I've shown with the Newman projection up top, anti-periplanar. And if we take a base and deprotonate this hydrogen, that's removed. That bond then forms a pi bond, which we won't be able to see, but it's connecting the carbon in front to the carbon in back, creating that double bond, and the bromide leaves. So now your Newman projection looks like this. And if you just look at it from the bottom, it ends up showing that that would have given, in this particular example, the cis isomer here. Okay, now I'm gonna take a look at what if I wasn't looking at HA, I'm looking at HB. So if I just go ahead and create anti-periplanar for HB, which you can, you just rotate the bonds, then you can undergo the same sort of deprotonation and elimination. Bromine leaves, you get this alkene product, and you can see these groups are opposite, so you get the trans isomer. So my point is, if you look back here to the original compound, you have a leaving group and then you have two beta hydrogens. If you have two beta hydrogens, you have the potential to generate both cis and trans products. And I already told you that if you have the possibility to make both, the trans is favored. We are going to look at some examples where there's only one H that's in the right orientation, or just simply only one H, then in that case, only one type of alkene can be formed if it can get anti-periplanar. Okay, so we say this is stereospecific because the product stereochemistry is governed by the configuration, or you could think about it, the geometry of the starting alkyl halide. And it's actually, configuration is the better term because it does depend on where they are in space, up, down, dash, wedge, that sort of thing. Okay, so let's just practice this. You guys are going to do 2 problems, and you guys are going to predict the product. So predict the major product that forms for an E2 reaction when both of these are treated with a strong base. So just pause here, work out these problems, and then come back and I'm going to go over it. Okay, for problem A, you have this bromide here, and you need to look to see if there's any beta hydrogen. There's some here. These are all methyl, so nothing here. So what's interesting is this is what we call a methylene unit. So it has 2 H's, just like the previous example I gave. So we know at least one of them can get into the antiperiplanar arrangement, and actually both of them can. So you can get your alkene product here. And your options are cis or trans, and you're going to prefer to make the trans product here. The next is this compound. So this is a little bit different because now I'm showing you a bromide that can, or a bromine that can leave, and this hydrogen doesn't come into play because it's on that same carbon. I need the hydrogen one more away so I could deprotonate. This sigma bond becomes the pi bond, and then this leaves. So I'm only looking at this Br and this H. We have to see, do we have the right configuration for it to be antiperiplanar? And I've already written it out like that. So this is antiperiplanar. They're in the same plane and they're opposite each other. So it's already set up to do the elimination. So what you do is just look at what's both on the same side. So your hydrogen's going to get deprotonated, bromine leaves, you form a double bond. But the real question is, where are the substituents? My tip for you here is the phenyl and hydrogen are both up on the same side, so they'll both be on the same side along the double bond. This methyl and tert-butyl, they're both down, so those will be both on the same side as well. So this is the product that you get out. Okay, cyclohexanes have stereospecificity as well, and this is because the ring can lock the geometry in place. And we'll talk a little bit about the nuances with chair flips as well. The key here for the elimination, E2 specifically with cyclohexanes, is this can only occur when the leaving group and the H being deprotonated are in the axial position. So that's why this gets interesting and stereospecific. So this compound here, chlorine's up, and so I can draw Newman. That's really not necessary for these problems, but I just want to highlight the chlorine is up and there is a hydrogen straight down. So this is antiperiplanar. This works, you can do your elimination. When the chlorine is equatorial, this is off to the side. You cannot have a hydrogen here, a carbon's here. So you cannot get a hydrogen antiperiplanar. That's why the equatorial halide will not undergo the E2 elimination. So what we're going to do is look to see with some substrates, can you get the leaving group in H antiperiplanar? If you can, you could do the elimination. Okay, so here we have 2 different conformers of this chlorocyclohexane. Equatorial is preferred for low energy conformer because the equatorial doesn't feel the A13 strain of a hydrogen here or here. That being said, that makes this lie to the left. There's more of the equatorial, but there's still some of the axial. And if there's some of the axial and a hydrogen can be antiperiplanar over here, these are antiperiplanar straight up and down, then you can have an elimination occur. So in this case, it will react to give elimination here. And as you keep consuming this, you could keep funneling a little bit, just naturally the equilibrium will shift. If you remove product, it'll shift to the right as the reaction proceeds. So what we want to do is now look at certain compounds and see if that can happen. Okay, so which proton is abstracted in the elimination? So you have two H's on either side of this alpha carbon off the chlorine, and only the red ones. If the chlorine is straight down, only the red H straight up, and this other one here on the other side, the red H straight up axial, only those two can participate in the E2 reaction. So you could deprotonate here, give the double bond here, deprotonate here, give the double bond here. Those are identical products. So that's your product here, cyclohexene. How about this guy? Will this undergo E2 elimination? And if so, what's the product formed? So pause this, take a moment to think about it, draw a chair structure, and make sure your chlorine draw the correct chair structure. You might have to play around with flips or whatever, but make sure your chlorine is up and axial. So you could just actually place it around the ring till you find one that's right. Okay. So basically, you need one where the chlorine is up and the hydrogen is down. And you actually didn't have to draw the chair. It's just really good to visualize that. But if you could get chlorine straight up, straight down, which we know next to each other, those are both axial. You could do a chair flip where they're equatorial, but still you can, again, even if the equilibrium doesn't lie in favor of the axial, that's okay, because a little bit will react. So the one that's going to react is this hydrogen. The reason is chlorine up and H up, that does not react. Those cannot be antiperiplanar. And there's a methyl here. So the only hydrogen that will react is this one, which is this down one here. You add a strong base, you deprotonate, form the double bond here, chlorine leaves, you get this product. And I just redraw it here. So this tip here is at the top of the cyclohexene, and then to the right is a methyl down, shown here. Okay, we're going to look at a disubstituted cyclohexane, and you guys are going to decide which elimination goes faster. So you could possibly have elimination for both. There may be one or more products. So what I recommend is for you guys to pause this, draw the different chairs, figure out which ones can undergo elimination and which hydrogens can undergo elimination, and write out the products. Okay, so for this first top one, where isopropyl's up and chlorine's up, you get two different types of chairs. So I'm showing two chair flips. You can draw one where the chlorine is equatorial and the isopropyl is axial, or chlorine is axial and isopropyl is equatorial. The one on the right is more stable and preferred because isopropyl has a bigger A value. It'll feel more A13 strain if it's axial versus chlorine. So this is preferred. So then you can look, okay, is the chlorine axial? Yeah, it is. Are there any axial antiperiplanar hydrogens? There are. So this is actually looking really good. Basically, this equilibrium is shifted to a side where it's already ready to undergo an E2. If you look at this compound below, you see isopropyl up, chlorine down. So you can have both diaxial, which we know is very unfavored because both will have the A13 strain. And then you can also see that diequatorial is favored. So this will not undergo the E2, the axial chlorine will, and with the axial hydrogen here. And it can happen, but there's very little substrate here at equilibrium. It'll happen as you react it, the equilibrium shifts to give more starting material to react with. So the upper compound will undergo E2 faster. The rate will be faster. The rate of the lower one is slower. So predict the products. I'm gonna bring you back to the chair structure that can react, the chlorine up. There are 2 beta hydrogens that are acyl that can react. So the first one I show is deprotonating this H to give a double bond here. And then in the next carbon over, an isopropyl is up. So you have a double bond in the ring, the next carbon over, the isopropyl is up. You can also deprotonate the second hydrogen on the right. That makes the double bond here, and chlorine is kicked out. So that double bond is directly attached to the isopropyl group here. So you could get these 2 products. The second compound, the only conformer that will react is this one where the chlorine is down, and there's only 1 hydrogen axial that can undergo E2 because there's no hydrogen here. There's an isopropyl group instead. So you'll only get 1 product, this product shown here. Okay, so predicting E2 reaction products is a little bit more complex than SN2. You have to consider regiochemistry as well as stereochemistry. Regiochemistry, again, is which proton is being abstracted. Just ask yourself, do you have a bulky base or not? Because bulky base will prefer the Hofmann, less substituted. Smaller bases, you'll prefer the more stable Zaitsev, more highly substituted alkene. Stereochemistry, are you getting cis or trans, or maybe it's E or Z, or both? You have to consider hydrogens available and antiperiplanar arrangements. So let's just end with predicting major products for the following E2 reactions. So just notice the bases used and just write your products. Okay, pause and then I'll go over this. Okay, so this first compound, you have a bromine up and you have 2 hydrogens, 2 types of beta hydrogens here and here. Since you have a small base, you'll prefer to form the more substituted double bond. So you'd want to be able to deprotonate here if there is an H that can be antiperiplanar. So if you draw the skeleton like this, a straight bond, and then you have a bromine up and H down, that is antiperiplanar. So what I recommend is just keeping the skeleton straight lines intact. And you can see that here, these straight lines are intact, and you do your elimination. So you deprotonate this H, you form your alkene here, and the bromine leaves, and so you have your methyl up, the cyclopentyl here, and just the rest of the chain is the same. Okay. In this lower problem, you're using a bulky base. So right there, when you see that, you have to start thinking, okay, Hofmann product, I'm gonna pick off the more available H's. I would love to make the more substituted alkene, but I'm just too big and I just cannot get in here. So I'm going to pick off the hydrogens that are more on the outside, the periphery. I'm going to deprotonate one of these and form a double bond, kick out iodide, and I get this product. Again, doesn't matter which methyl you deprotonate, you get the identical product. If you just do a bond rotation here, you get the double bond down here. Okay, that's where I want to end. The next time we're going to just bring it all together and we'll be able to really predict whether SN2, SN1, E2, E1 are going to occur.